Hello and welcome everyone. Let's continue solving the Schoenprasad patterns by tackling the list link cycle problem. We are given the head of a linked list and we want to determine if the linked list has a cycle in it. And basically we know that a linked list is supposed to, we know that we've gotten to the end of a linked list when the tail doesn't point to any other valid node, it points to none. But in the case of a cycle, there is not going to be a tail. All we would have is this endless loop where the linked list points to another node that already exists in our linked list. So that is how we determine that indeed there is a cycle. And so we're just going to give ourselves more room and tackle this problem. We will be approaching this problem in two different ways. The first is the intuitive approach, right? Using a hash set. We use our hash set to keep the address to the visited node basically. So we go through the first element, we save it in our hash set. If it doesn't already exist, we go through the second node, we store it in our hash set basically, and we'll not be storing the value nodes, we'll not be storing the value, we'll be storing the node. And basically this just means we're storing the address to the node, not the entire node itself. And then we traverse, we store a number in our hash set, and then we go back and we check, because before we store we have to check if this node, the address to this node already exists in our set. And in this case we can see that this address already exists, and we're just going to return a true that indeed we have a cycle. And this is the most intuitive approach, because we know that when we are looking for duplicates or cycles or basically anything that is repetitive in a problem, our first instinct is to use a set to keep track of the things we have visited, and then we can always check if this current element we are on is an unvisited element. If it isn't, then we know that okay, we are not in a cycle, but if it is, we are definitely in a cycle. This uses a O of n time complexity, since we are traversing all of the possible items in the all of the possible given items to find a duplicate. And it also uses an extra memory. This set is an extra memory, and that is O of n space complexity. Now there is a way we can do this in constant space, still linear time but constant space rather, using the Floyd cycle detection algorithm. And this algorithm just basically states that there is a mathematical proof for this. In a cycle, if there are given points, one is moving faster than the other, but they are both moving, eventually they are going to meet at the same point. That is what the theory is about. It's just saying that if there are 2 points moving, one is moving faster than the other, eventually they are going to meet if the plane is indeed a cycle. If it's not a cycle, then they might not meet. But if it is a cycle and one is moving faster than the other, they are both moving, but one is moving faster, then eventually, because it is a cycle, they are going to meet. And so we'll be translating that cycle detection algorithm into this code for our own use. Now we can just check how this works basically. So let's say we have a pointer that moves slow and a pointer that moves fast, and let us say this slow pointer moves at the pace of, it takes 1 step, right? Its first steps, it lands here. But our fast pointer, it takes 2 steps, unlike the slow pointer that takes 1 step. Our fast pointer takes 2 steps and it lands here, right? Now they are still moving, they are still the same, nothing is changing. And then our slow pointer goes ahead and take 1 more step, and we can see that this is where the slow pointer lands. But recall that our fast pointer, this is the first loop, the slow has gone, the second has gone. Now this loop, we want to check if they are moving at the same time. Now this also moves, it takes 1 step, because recall that our detection algorithm, this is where this is pointing, right? So when our fast pointer takes first step to 2, this is where it lands, then takes a second step to 4, it eventually meets the slow pointer. And if at any point they've met, we can return that we indeed have a cycle. Now this is how both works. We're going to be coding them both up to just see how it translates to code. Now the first one we'll be using our cycle, we're using our sets data structure to keep track of visited sets, right? And while we still have head, while there is head, we want to check if head is in our set. If it is, we want to return that indeed we have a cycle. If it isn't, we want to add the head to our set, and we also want to move so we don't get stuck in an infinite loop. And we can just return false if we've come to the end of our linked list and there is no cycle. We're going to run this and just to make sure that it works fine. And we'll just submit it since this already passes the test cases. We can submit this and we see that this actually runs. Cool. Now we're going to be using the Floyd's detection algorithm to test this, and we know that we need 2 pointers, a slow and a fast pointer. Since they both point at the very beginning of the linked list, we can change them like this in Python. If your programming language does not allow this, then you just assign them differently. Slow is equals to head, fast is equals to head, but we are starting at the same point, right? Now while fast is valid, while fast still exists, because fast is going to run, we said that one of our algorithms is going to run faster than the other, and we've kind of like mentioned that it's explicit now that fast is running faster than slow, definitely. Now if fast is null, then there is no need, we know clearly that slow is going to be null. So that is why we're using fast to check if fast is still valid, right? Then we still want to continue checking that there is indeed a cycle for as long as they've not yet met and this fast is valid. We want to check that. Okay, while fast dot next, we want to move our slow pointer by one step, and we are moving our fast pointer 2 steps ahead. And if at any point slow is equal to fast, then we want to return true that we have found a cycle. Otherwise, if this condition is no longer true and we still haven't found the cycle, then we know definitely that this is false, and we can just submit this to be sure that it works. And again, we can see that this works. I hope this was explanatory. It might take a little bit of digging around to really come to terms with how the Floyd cycle algorithm, detection algorithm works. But once you get the hang of it, it's going to help you with a lot of linked list problem. So I think that is a understanding how this algorithm works, the Floyd cycle detection algorithm, is a basics for really moving on with your linked list knowledge. I'll see you in my next video. If this was in any way helpful, please subscribe. It helps to support the channel. Bye.